Hello. In this video, we're going to look at limits at infinity, section 2.6 in your textbook. And the motivation for this section would be the following question. What is the value of 1 over x as the graph extends far to the right? So here we have the graph, just the portion when x is positive. Of course, there'd be another swoosh down here, but we're just looking here. And as we go further and further and further and further to the right, well, what's happening to the graph? What's happening to 1 over x? Does it appear to be approaching something? Well, if you remember from pre-cal, we often would draw on the graph a horizontal asymptote. And that horizontal asymptote is helping guide our graph that as we move to the right, the graph is approaching that asymptote. It's approaching the value of the asymptote, which in this case is 0. And we can think about this process of approaching again through the lens of a limit. So normally for our previous limits, we were approaching a specific value like 1 or a half or 0, and we were seeing what happened to the graph. For example, in this case, as x approaches 0 from the right, the graph would approach positive infinity. But in this case, we're not going to be approaching a specific value. We're going to be extending far to the right and saying, as we go off to infinity on the right, does the graph approach a specific value? So our definition would be as follows. Let fx be a function defined on some interval a to infinity. Then the limit as x approaches infinity of f of x will equal L, and what this means is that the values of f of x can be made arbitrarily close to L by requiring x to be sufficiently large. So let's look at our example. Let's calculate the limit as x approaches infinity of 1 over x. So we could plug in, for example, x equal to 10, and that would give us a value of 1 over 10, which would be 0.1. You could use your calculator to check. Or 100 would be 0.01. 1,000 would be 0.001, and then 10,000 would be 0.0001. And so we can see that in this case, the values of 1 over x are getting closer and closer and closer and closer to 0. So we could say, based on our calculations here, therefore the limit as x approaches infinity of 1 over x equals 0. As x gets larger and larger, as we go off to the right, the values of 1 over x are approaching the value 0. So what if we were to look at the limit x approaches infinity of 2 over x to the 5? Well, the first thing we're going to do is factor out that 2 because constants can factor out of limits. So we're going to put the 2 in front and then consider this quantity, 1 over x to the 5. Now, as x approaches infinity, what happens to the quantity 1 over x to the power of 5? Well, you can think about plugging in 10. 10 would be, 10 to the 5. So 1 over 10 to the 5, that's going to be a very small number. Or if x becomes 100 or 1,000, you're going to have 1,000 raised to the power of 5. And then you're going to do 1 over that number. That's going to be very, very, very small. And so this quantity is going to approach 0. So 2 times 0. Which of course gives you 0. And so if you were to graph 2 over x to the 5, you would find that as x approaches infinity, as you move far to the right on the graph, you're just going to approach 0. Now, what if we went to negative infinity? Well, let's think about it. The negative 7, of course, is just there as a constant. We can factor that out. So we'll get negative 7 times the limit x approaches negative infinity of 1 over x to the 7. Now, we have to think about taking very large negative numbers, so large in the negative direction. Let's say we picked negative 100. Well, negative 100 to the power of 7, it's still going to be negative, but it's going to be a huge number. It'll be a huge negative number, but when you do 1 divided by a huge negative number, you get really close to 0. And so this quantity, again, is going to be equal to negative 7 times 0, because this is approaching 0. And of course, that'll just give you 0 in the end. Now, what you want to think about here, and Again, please don't ever write this down, but this is something you can think. If you have 1 over plus or minus infinity, right, in this case you can think about it, you're almost like plugging in the infinity. You've got 1 over infinity or 1 over negative infinity, 1 over a very large number, increasing. That's going to ultimately go to 0. So you can think of 1 over 0 as equal to 0. Now never write equal to 0 because infinity is not a number, but you can think about it like approaching 0. And it's actually just the same version that we had before. Remember 1 over 0, that always gives us a plus or minus infinity? So it's the same idea, we've just sort of swapped this around. 1 over 0 gives us infinity, and 1 over infinity gives us 0. But again, never write equals to because, well, they're not really equal. Infinity is not a number. So this is just something you can think about. Now, if we were to just plug in for something simpler, if we had the limit x approaches infinity of maybe x, well, that would actually plug in as infinity, because as x approaches infinity, well, the graph of x, it doesn't approach a fixed value, it just keeps growing and growing, right? The graph of x is just a straight line. This is y equals x. And so as you move further and further to the right, well, the graph just grows and grows and grows. It just keeps going on and on and on to infinity. It doesn't ever approach a specific value. Or if you were to do the limit as x approaches negative infinity of x, you would go the other way on this straight line, and you would get, of course, negative infinity. So those limits should make sense. And if you had, let's say, a power of x, right? If you had the limit x approaches infinity of x to the power of n, well, if this was x squared or x cubed, again, you can imagine those parabolas. They're all just going to keep going on and on and on and on to infinity. So this would also give us infinity. But the tricky one is if you had x approaching negative infinity of x to the n. Because if it's a parabola, well, it's going to open up, and so as you approach negative infinity, it's still going to go to infinity. But if it was a cubic function, something like this, then as x approaches negative infinity, it's going to go down to negative infinity. So this is going to equal plus or minus infinity, depending if n is even or odd. So let's do some practice working with infinity. I know this is a bit of a new concept for many of you, so we need to go over some rules of infinity. The first thing is that infinity plus infinity is equal to infinity. Now, what this means is that if you're increasing up and up and up, your numbers are growing without bound, and then you add another quantity where the numbers are growing and growing and growing, together, they're still just growing. You don't somehow get to infinity or something like that. Infinity plus infinity is just going to give you infinity. Now, infinity times infinity is also going to give you infinity. And that should make some intuitive sense. If something is growing and you multiply by something else that's growing, they're both just growing. It might be growing faster, but it'll still be infinity. Negative infinity subtract infinity will be negative infinity. Again, that should make sense. But infinity minus infinity is going to be an indeterminate form. It's going to mean we need to do more work. And this is important because you might think that infinity minus infinity is just 0. But it's very important that you don't treat infinity like a number, because infinity is not a number. Now I'll show you what I mean by that. Let's say we treated infinity as if it was a number. So if infinity was a number, well, we could start with our quantity. Infinity plus infinity is equal to infinity. All right, well, we know infinity plus infinity, if that was a number, that would be to infinity. And then we could go ahead and divide both sides by infinity. and we would get 2 equals infinity divided by infinity would be 1. Well, there you go. In 3 lines, we've shown that 2 equals 1, which is, of course, ridiculous and absurd. And it means that you can't treat infinity like I did. Doing this process is incorrect because it leads to the incorrect statement 2 equals 1. Now, just as another note here, part of what I'm having issue with, of course, is infinity divided by infinity. This over here is also an indeterminate form. So coming back to our work over here on the side and trying not to break the rules of math, let's see if we can figure out the following limit. So we should probably put brackets around that. The limit x approaches infinity of 3x cubed minus 2x squared. So we can think about plugging it in. Well, here we'd have infinity cubed, which would be infinity. 3 times infinity would be infinity. And here we'd have infinity squared, which would be infinity, 2 times infinity. So this would be an infinity minus another infinity. Well, if we have infinity minus infinity, we know that we need to do more work. That's not valid. So what kind of work could we do here? Any ideas, any insights, any math technique that might be useful? Well, hopefully you're seeing it. We could go ahead and factor out a power of x. Well, in fact, we could factor out x squared. That'll leave us with 3x minus 2. Now here we go. X squared is going to be infinity. 3 times infinity is infinity, and infinity minus 2 is definitely infinity. So this is technically infinity times infinity, which is just equal to infinity. There you go. So the correct answer for this is not infinity minus infinity, it's actually infinity, which is really weird because you might have thought infinity minus infinity was going to be 0. But in fact, in this case, infinity minus infinity was still infinity. And what that means is, of course, this is an indeterminate form. It's not determined because one of the infinities might be larger or stronger than the other infinity. In this case, if you look, this infinity, the first one, came from x cubed. The second infinity came from x squared. So the first infinity was stronger than the second one. And so in this infinite tug of war, the first infinity won out and you actually got the answer of infinity. Now let's go ahead and try another one. We have x to the negative infinity and we have the following expression, negative 2x cubed plus 2x minus 3. Well, unfortunately, there's no x in common to factor. And if we were to plug it in, well, this portion we could see would be negative infinity cubed, which would be negative infinity, times 2 would be positive infinity. So there'd be a positive infinity here, but then over here there'd be a negative infinity. So this looks like infinity minus infinity again. So what in the world are we going to do here? We have some type of situation, but there's no factoring we could do. Well, actually there is. And so there's this method that I refer to as force factoring. I'll give you an example of force factoring. Let's say you had 2x plus 7. Do you think you could factor 2x plus 7? Well, initially you might say, no, there's nothing in common with the numbers and there's nothing in common with the x's. But I think you could factor out an x because you'd be left with 2 plus 7 over x. Now, that seems like it breaks all the rules, but let's go ahead and multiply back. X times 2 will be 2x. X times 7 over x will be 7. So because this multiplies back, this is indeed a correct factoring. It's not the factoring you're used to, and it's often not a very useful type of factoring in regular factoring world. But in this limit question, this is exactly the skill we need. So let's go ahead and factor out x cubed in the same way. So we have the limit. X approaches negative infinity. We're going to factor out that x cubed. So we'll get negative 2 plus 2 over x squared minus 3 over x cubed. Right? Let's see if it multiplies back. X cubed will go into that first term, giving me negative 2x cubed. X cubed will go into the 2 over x squared. So the x cubed and the x squared will reduce to just an x. And then here the x cubed will cancel with the x cubed to give me negative 3. So that looks good. Now let's see if we can go ahead and do our limit. Well, this is going to be negative infinity cubed, which will be negative infinity. The limit of a constant is still going to be a constant, so negative 2. Now 2 over negative infinity, well remember, when you have a number over infinity, you just get 0. And again, 3 over infinity, that'll also be 0. So we have negative infinity times negative 2. Well, just like with regular numbers, when you're multiplying infinity times a negative number, it does switch the sign. So negative infinity times negative 2 does give us a positive number. So the answer is positive infinity. Now we're going to go ahead and look at the graph here to make sure this makes sense. So here we have our polynomial. And we can see very clearly that as we go off to negative infinity, so as x begins to move left and continues to move left and left and left, the graph is going to go up and up and up to positive infinity. So the graph continues to increase as we move further and further left. So the limit would be indeed positive infinity. Now in general, we factor out the highest power of x to evaluate indeterminate forms for infinity limits. This is our general technique. So let's look at this one. We've got a bit of a crazy question here. X is approaching infinity of 5x to the 4 minus 2x plus 1 over 3x minus 2x to the 4. Now, in the numerator, this would be an infinity, because infinity to the 4 times 5 will be infinity, minus infinity. So already, right at the beginning, we've got infinity minus infinity. We need to do more work. No question about it. So let's look and factor out the highest power of x from both the numerator and the denominator. In the numerator, it looks like there's an x to the 4. So it'll be 5 minus 2 over x cubed plus 1 over x to the 4. It actually looks like the bottom has the same. The denominator also has a power of x to the 4 that we can factor, or force factor. That'll give us 3 over x cubed minus 2. And the work we can do in this case is we can also cancel out these x to the 4s. It's going to be quite interesting what happens when those cancel. So now we have the limit x approaches infinity of 5 minus 2 over x cubed plus 1 over x to the 4 all over 3 over x cubed minus 2. All right, well, let's try to plug in the limit. 2 over x cubed, that's going to give us a 0 because x is approaching infinity. 1 over x to the 4, that's going to be a 0. So, and the limit of 5, of course, is just 5. So 5 minus 0 plus 0. In the bottom, 3 over x cubed is going to be 0. So I've got 0 minus 2. So I have 5 over negative 2, or negative 5 over 2. There's my answer. Now, if you take a step back and look at this question and pretend there was no limit, and you were asked from pre-calculus, what is the horizontal asymptote of this function? You might remember some rule about if the top has a higher degree or the bottom has a higher degree, or if they're balanced. And in this case, they're balanced. They're both degree 4. Well, when they're balanced, you're supposed to take the coefficient of the numerator over the coefficient of the denominator, the leading coefficient, the one from the highest power of x. So using pre-cal, from pre-cal, you should just get a horizontal asymptote at y equal to 5 over negative 2, which, if you notice, is the same as our limit. Now we're going to draw more conclusions about this in a future video, but for right now, notice that this horizontal asymptote idea and this limit as x approaches infinity are giving us the same answer, the same number, 5 over negative 2. And that's going to be important as we move forward. Now, this idea of force factoring out is a little bit cumbersome. It creates a really giant piece of math to work with. And because it's the same every time, we can actually prove a theorem to speed this up a little bit. So the theorem is called the Quotient Theorem. Now it looks, I'll admit, a little bit nasty because there's so many letters. But once we prove it, it's going to make our math a lot easier as we do these questions. So the Quotient Theorem says the following. If we have a function that is a rational function, a polynomial over a polynomial, so an x to the n, an minus 1 x to the n minus 1, all the way to a0, bm x to the m, bm minus 1 x to the m minus 1, all the way down to b0, of course where the leading coefficients are not 0, then the limit of the function is going to be equivalent. So notice here we have 3 equals. That means equivalent in math. Sometimes I think about it like a super equals. It's like more equal than equal. It means that they're equivalent forms. So in this case, these two will be equivalent if, well, we have polynomials. As long as this and this are our polynomials, we can always replace our function with the following, which is just an x to the n. If you notice the very first term, that leading term, and bm x to the m, the leading term of the denominator. So let's look at the proof. So we have the limit x approaches either one of the infinities, plus or minus infinity, of fx. So it'll be the limit x approaches plus or minus infinity, and we'll write this whole function out. An x to the n, an minus 1 x to the n minus 1, plus a0 over bm x to the m plus bm minus 1 x to the m minus 1 plus b0. All right. Now what we're going to do is factor out the highest power of x, just like we did on our other questions. So here there's an x to the n that we can factor out of all of these, and here's there's an x to the m that we can factor out. So we will get the limit as x approaches plus or minus infinity, x to the n, an plus an minus 1 over x plus a0 over x to the n divided by x to the m bm plus bm minus 1 over x plus b0 over x to the m. Now as we do the limit, each one of these terms is going to disappear, because as x approaches plus or minus infinity, this is 0, all the ones in here are 0, this is 0, all the ones in here are 0, this is 0. So each one of these is approaching 0. Now we're not going to do the rest of the terms in the limit. We're going to still leave the an and the x to the n. We're going to leave those for right now, but we're going to consider how those terms approach 0. So rewriting this, we would have the limit x approaches plus or minus infinity of x to the n, an plus 0 plus dot dot dot, a bunch of zeros, over x to the m, bm plus 0 plus dot dot dot, a bunch of zeros. Now, of course, those zeros we can just get rid of, and so we'll have the following. The limit x approaches plus or minus infinity of x to the n an over x to the m bm, which usually we write it with the constant first. So x approaches plus or minus infinity of an x to the n over bm x to the m. And there's our proof. We've shown that the function on the left-hand side here is going to be equivalent to this version on the right-hand side. So we can now redo our example nice and quick. So let's go ahead and redo that example we were looking at before. So we had the limit x approaches infinity of 5x to the 4 minus 2x minus 1 over 3x minus 2x to the 4. So we're going to use the quotient theorem. Now, to help illustrate that we're using it, we often write a little QT above the equal sign, just so the people reading our work know where all the other terms went. They disappeared because you can drop them all. You can keep only the powers that are x to the 4 in this case. All the other terms, you just get to drop them. So we write quotient theorem, little QT there, and we get the limit x approaches infinity of 5x to the 4 over negative 2x to the 4. Cancel out the x to the 4s. So we have the limit x approaches infinity of 5 over negative 2, and the limit of a constant is just the constant itself. So there we have our answer again, a lot more quickly using the quotient theorem. So let's go ahead and do another example here. We have the limit x approaches infinity of 2x plus 1 to the 3, 4x cubed plus 7 over 2x to the 6 plus 6x. Now if you were to plug this one in, you would get an infinity here, 2 times infinity plus 1 cubed, that's infinity. You'd get an infinity here and an infinity here. So you might be tempted, because infinity times infinity is infinity, to just say, well, the answer will be infinity. But the top is infinity and the bottom is also going to be infinity, which means that we need to do more work, because infinity over infinity is not going to be 1. We have no idea what infinity over infinity is. It might be infinity, it might be 0, it might be 5. We have to figure out what it is. And so we will use our quotient theorem to get the following. X is going to approach infinity. We can drop the 1 and just keep the 2x. We kind of have to use the quotient theorem individually on each part because they're all being multiplied. So we drop the 7 and keep the 4x cubed. And here we drop the 6x and just keep the 2x to the 6. Now make sure that when you cube this, you cube the 2 and cube the x. So that'll be the limit x approaches infinity of 8x cubed times 4x cubed over 2x to the 6. Now thankfully x to the 3 times x to the 3 will be x to the 6, so we can cancel those out. And we'll get the limit x approaches infinity, 8 and 4 will be 32. Well, the limit of a constant is just the constant, and 32 over 2 is 16. So it turns out that infinity over infinity is actually 16. Again, a little surprising, a little shocking, but that's because this is an indeterminate form. It needs to be worked on more. And in this case, the work we do is the quotient theorem. So go ahead and determine the limit as x approaches infinity of x to the 7 minus 4 over x to the 6 plus 8. Go ahead and pause the video and give it a try. Alright, so hopefully you gave this a try. Again, because x is approaching infinity, we can use the quotient theorem. And we'll just drop the 4 and the 8 to give us x to the 7 over x to the 6. When you cancel those out, you're still going to get x to the power of 1 on top. So we'll have limit x approaches infinity of x, which is going to be infinity. So the answer is D. Now for homework, go ahead and try your limits at infinity part 1 worksheet. But don't do the ones with the square roots yet. We're just going to hold off on those until we look at part 2 in our lesson, because the square roots require another little technique that we haven't learned yet. But you can go ahead and do all the other ones on that worksheet. So hopefully you enjoyed this video, and as always, thanks for watching.